English. So we basically completed the discussion about black holes last time. And so introduced the Kruskal Seker's coordinates, and we saw what the... So, just to make sure that you're all, you feel comfortable, right? What did we do with black holes, right? We started with standard coordinates, T and R, right? And we saw that they don't represent what happens properly smaller than the Schwarzschild radius. Then I did some manipulations, and we ended up with the Kruskal Seker's coordinates. And we saw that in these coordinates, everything is very well defined, well behaved, fine. But then some of you was kind of like, I'm happy with how did I bypass the mathematical problem? And the correct answer is I didn't really even have to start from T and R, right? I could start from Kruskal Seker's coordinate, right? U and V, or capital T and capital R, and plug it into Einstein's equation and solve it with that, and then I would not have any problem in the first place, right? So and then I can express my T and R in terms of the Kruskal coordinates, which is a perfectly legitimate thing to do. The thing is, both derivations give us some very important physical insight, right? So when I work with T and R, the physical insight that we get was that from an external observer's point of view, from our point of view, we will never see anything crossing the event horizon, right? And then we work with the Kruskal Seker coordinate, we got the two other important insights, which is, one, there's really no problem crossing the event horizon. From the point of view of somebody who wants to get in, they would get in. And two, once you cross this Schwarzschild radius, then there is no way back. You could never return. One way to think of it, the only way to return is if you can move faster than light, which you cannot. These are the main insights, and because of that, the Schwarzschild radius is also called the event horizon. What happens at the singularity r equal to 0? The correct answer is I do not know, because the laws of physics stops to be valid just before that. But you will not survive, so don't really care. Okay, and then we move on to the next subject, which is cosmology. So I have to warn you that unfortunately we'll have a little bit of technical class today. I could avoid it, but I don't want to, because my approach is to give you everything, so you see that I'm not lying or cheating. Yeah?
יכול להיות שאני מערבב קצת, כשדיברנו על האיבנט הורייזון, אמרנו שנגיד בשמש, זה לא בעיה, כי זה נמצא, שני GM זה בתוך השמש, והשיעור של ניצול שלא רלוונטי שם. כשדיברנו על חורים שחורים, אז אנחנו מדברים עד R שווה 0. איפה נכנס
What we said about black holes, we said we may have objects in which the size of the object is smaller than its Schwarzschild radius. It has to be very dense. Of course, in our sun, the radius of the sun is larger than the sun's Schwarzschild radius. Right? The Schwarzschild radius is linearly dependent on the mass, only on the mass. The rest is just physical constants. Right? So it's really a question of density. So in principle, you can think of miniature black holes. Just have to take some material and compress it so hard, so much that all its mass will be squeezed into a region which is smaller than its Schwarzschild radius. Yes, but for every given mass, I can think of the Schwarzschild radius of myself, right? My mass, therefore I weigh, I can squeeze it into the tiny region. It will become a black hole.
כשדיברנו על חורים שחורים, דיברנו עד R שווה 0. אז הרדיוס של החור השחור צריך לקבוע לאיפשהו גם.
I said, close to R equal to, we gave the mathematical solution. Mathematical solution, classical mathematical solution. I did not speak about quantum mechanical effects or really quantum field theory effects that might get in. I'm not talking about quantum gravity. The only thing I said is that when we reach very close to the singularity, the laws of physics as we know them, doesn't matter which theory, fail to be relevant. They're no more relevant. And in that case, you know, everything I say, I can say whatever I want, but it's meaningless. Right? If we speak about physics, then the laws of physics we know that govern our life stops being valid. Now there are theories that says that they will be stop being valid, you know, even larger radius, maybe close to the Schwarzschild radius, if you now start involving quantum mechanics. One, I'm not an expert in that. Two, I don't fully trust what I read and what I heard about the things. So anyway, this is not part of the course we're supposed to be teaching. Okay, that answers the question. More on that? No? Okay, so we start to move to talk about cosmology. We said there is a question.
It's kind of related to the question asked earlier. If you have a black hole, you have a mathematical stuff, and an astronaut could enter into the black hole.
Yeah.
How? Because our black hole.
Will we enter into the black hole means cross the Schwarzschild radius.
Yeah.
Yes.
So, in our metric, for example, for RT and theta and phi, it just we had an astronaut and then we didn't. Or no?
No, we will never see an astronaut crossing the event horizon. That's the thing. If you have an astronaut, and we demonstrated that last time, let's say there is an astronaut that is crossing the black hole and he's sending us signals telling us, I'm okay, I'm okay, I'm okay. What's going to happen is that you'll see the signals getting slower and slower and redshifted, but you will never see the point where this astronaut actually crosses the black hole. It's a vague infinity. Okay, so cosmology. So we said that the modern cosmology is based on the cosmological principle, which by itself is a modern development of what's known as the Copernican principle. Right? So Copernicus said that we are not in the center of the universe, and the modern cosmological principle states that the universe is homogeneous and isotropic. The universe is homogeneous and isotropic. Homogeneous means every place we are going, it looks the same. Isotropic means in every direction that we're looking, it looks the same. Again, this is not true on smaller scales, but when we go to a very, very, very large scales, as far as we know, we believe this is true. And the only caveat is that this is true from the spatial part, from space. When we look at the time, we do see an evolution. We'll discuss that. I mean, the first, of course, was Hubble to see that galaxies seems to move away from us. So if we now take that...
so it's the spatial part of the universe is homogeneous and
yes, in reality. But for now, the discussion is going to be general. So we're going, the purpose of today is to derive the metric that will describe the universe that is homogeneous and isotropic. And I can put it in, or instead we can go over the long way, which we're going to do, and we're actually going to derive it mathematically. And mathematically, when we say homogeneous isotropic, what we mean is this is translated into a maximal, what's known as a maximally symmetric space. This is equivalent to maximally symmetric space, which intuitively is what you think it is, right? A sphere is a maximally symmetric two-dimensional space, while an ellipsoid, like American football ball, is not a maximally symmetric. It does have symmetry, but it's not a maximally symmetric. So mathematically, maximally symmetric space means that it contains the maximal possible number of Killing vectors. maximal contains maximal possible number of killing vectors. And when we speak about an n-dimensional space, I'm not going to prove it because the exact proof is a bit annoying, but intuitively it's very easy to understand that this maximal number would be n for translations for n-dimensional space, n translations plus n times n minus 1 over 2. This is rotations, right? And axis, and then I choose another axis, and if I rotate from x to y and from y to x, it's the same, so I have to divide by 2. Yeah?
But you said that the universe is only the spatial part is homogeneous.
Yeah, right now it's a complete general discussion about maximally symmetric spaces. So
we're
technically,
not talking about the universe.
not that way. Technically, what we will really develop, the universe is a space with a maximally symmetric subspace. But let's not overcomplicate things. Right now, let's look at the properties of a maximally symmetric space, and then we plug it into where we need it. But the discussion is general. Okay, so overall, of course, this is n plus 1 over 2 killing vectors. As you know, when n is greater or equal to 2, you already have more killing vectors than dimensions, which is not a big issue. Okay. So in order to derive the properties of a maximally symmetric space, I'm going to have a look at a few more properties of killing vectors. Okay, so for now, I'm just going to leave with that, right? Maximally symmetric space. See if I need to get your pens. This pen is so weird. Okay, questions about that? Before we start digging into the algebra, it's a little bit annoying. It's the kind of thing that you catch like, you see, go over it. It's one of those things that you'll have to go slowly. I mean, I went over it and checked everything. It's fine what I'm going to give, but it will take you. Have to revise it to see it. I'm not cheating you. Okay. So. So the general discussion now is about maximally symmetric spaces. And what I want to do is to give a few properties of killing vectors. Or more properties. We already discussed killing vectors, we saw a few properties. So, ready to algebraic. Okay, so killing vector satisfy killing equation. K sigma rho plus K rho sigma is equal to 0. First, the second thing we know about killing vectors is that they are vectors. Being vectors, right? You can go back to the defining property of the curvature tensor. Right? You remember that the curvature tensor was defined when we look at the commutator of two covariant derivative of two vectors. Right. What is that? This is equal to K sigma rho mu, right? Minus K sigma mu rho is equal to what? Yeah, it's a lower, so there is a minus here. Right? This is true for any vector, not just a killing vector, right? Minus r lambda sigma rho mu k lambda. Remember that? We derived that when we spoke about curvature. Okay? If you don't remember, go there. This is true for any vector, in particular for a Killing vector. Okay, now we have the cyclic sum rule of the curvature tensor, right? So we had R lambda sigma rho mu plus R lambda mu sigma rho plus R lambda rho mu sigma is equal to 0, right? Remember that? We derived all these things. Okay, so I'm going to use that in here. Then I find for basically any vector, right? Not just the Killing vector, but any vector. I can just add up these terms to get a 0. So what I'm going to get is a k. So use that in here. And we got that k sigma rho mu minus k sigma mu rho. Now I switch order plus k mu sigma rho minus k mu rho sigma plus k rho mu sigma minus k rho sigma mu is equal to 0. We just plug it in here. Again, true for any vector, not necessarily a Killing vector. Now I'm going to use the Killing condition, which is written here. Okay, sigma rho plus k rho sigma is equal to 0. Right? So that is equal to that. It's really twice, right? And then that equal to that. So again, there's a minus. Then that goes with that. I plug in the Killing condition here. So overall, I get k. So they're equal, so I can just remove that and multiply that by 1. So I have 2, 2, 2, so I can divide by 2. So it's a k sigma rho mu minus k sigma mu rho minus k mu rho sigma is equal to 0. Now I use that again in here, right? Because I have this commutator, k sigma rho mu minus k sigma mu rho, which is just k mu rho sigma. So I have that the k mu rho sigma is equal to minus r lambda sigma rho mu k lambda. So I promise you it's going to be a little bit mathematical, but you know it's pretty straightforward. Okay, it's really algebra, right? What I'm doing here. Again, I'm doing it for a good reason, which is to derive some result, which at the end will look trivial, but I want to put it on one thing. Yeah? That was easy to follow. If it was not easy to follow, you tell me. Okay, so now let's do the same thing. I don't use that anymore. I'm going to erase it anyway because I want to have space.
Don't you have a minus?
No.
Because you have 2 minuses.
No, it's plus, minus, plus. Then the minus might move to the other side.
But it's minus. Well, but the first equation was minus. No.
The minus stays. It's fine. I told you. If you want to fully do it slowly, you have to go and follow it and do it at home. I'm not cheating. This has been tested. Just do it slower than what we do here. Okay, now I repeat back again the definition of the curvature tensor. But now with k rho mu, which is k rho derivative of mu, which is also a tensor. So again, from the definition of the curvature, we have k rho mu sigma nu minus k rho mu nu sigma. Now I'm going to have two terms on the right hand side, right? We have minus r lambda rho sigma nu k lambda mu minus r lambda mu sigma nu k rho lambda. Again, it's the same thing. I took the commutator, but now of the tensors k rho mu. Yeah. Derivative with sigma, then derivative with rho with nu, and commutator, and again the same formula that we used before. And then we have this equation which is written here. So we take that equation and we take its derivative, and now I'm doing something which is a little bit nasty. So I'm just switching a few things at the same time. So what am I doing? I'm taking this equation. Now I'm replacing mu and rho. Mu is exchanging with a rho. Sigma is exchanging with a nu. And I take the derivative of that, and I get and I switch side as well, just to confuse you or myself. I don't know why I decided to do three things at the same time. And I end up with an r lambda sigma rho mu k lambda mu minus r lambda nu rho mu k lambda sigma plus, now I take the derivative of here, r lambda sigma rho mu, derivative is nu, minus r lambda nu rho mu, derivative with sigma. Okay, lambda is minus r lambda rho sigma nu. I'm just copying k lambda mu minus r lambda mu sigma nu k rho lambda. Okay, what did I want to do? I just took that and I want to plug it in here, right? So the right hand side I just copied. The left hand side I switched first rho and mu, right? So as rho and mu is switched, and then I took the derivative with respect to nu, right? So switch rho and mu, take the derivative with respect to nu. So I have two terms, one lambda nu, which is that, right? So first term kappa rho mu sigma nu is minus r lambda rho and mu sigma nu rho with respect to sigma k lambda minus r lambda sigma mu rho k lambda. So this term is here. I switch mu and rho again, so I get the plus sign here, and this term here is exactly what's written here.
It's supposed to be mu the first stop.
No. No. I just switch mu and rho. Switch mu and rho.
No, in the
Go
equation.
in the second term.
You
Yeah,
leave the
after the
sigma.
equation, you
What, this
divide.
one? Oh, because I switch.
No,
I
No, the
sigma.
derivation is
The
called the
index
sigma
sigma
is the new.
feels twice. יש לך סיגמה פעמיים. סיגמה
איפה?
סיגמה סיגמה.
אתה גוזר לפי סיגמה.
No, it's supposed to be mu and then sigma because you have the other one over there.
No, then there is the other one which I have the minus sign. I just plug it in here. Right? So the
Just
first term
plug
will just be these two, and
same.
then the second term will be these two, and it will work. That's why I told you to do it.
Wait, but you just wrote it the same thing. You have minus r lambda sigma.
Ah, and then I change order, so I get the plus.
No, but in the equation, you just wrote the same thing. You have sigma mu rho mu, and then you have sigma mu rho, and again mu.
No. First, I took the derivative with respect to sigma.
Okay.
Sorry, I took the derivative. Sorry, I took the derivative with respect to mu. So I have the first derivative, the r derivative with respect to mu times k plus r k with respect to mu.
Okay.
No, that's fine. Again, I'm not cheating, but it can be a bit confusing. It's okay, I've been checking it multiple times. And again, there can always be a typo. It's very rare these days, but you find one, so you can find another one. I challenge you. Okay, right, so I take that, I take this equation, I take the derivative, I plug it in here, I switch, I plug it in here, that's what I get. Good. Now I'm using again the killing condition. I'm using again the killing condition. So k alpha lambda is k lambda alpha. Alpha is anything here. It's minus k alpha lambda, right? Alpha is anything. So I have, let's see. I am giving that. This I move, okay. Now I'm switching orders again. So this will be in the right hand side. You can think of it on the left hand side. I just put it in the right hand side, and then I move this one to the right hand side, these two terms. So this one is just going to be what it is, r lambda sigma rho mu minus r lambda mu rho mu sigma rho mu sigma k lambda. And this ones I have minus r lambda rho sigma mu. I have a k mu lambda. So I write it as a delta kappa mu k lambda kappa. That's fine. Okay, I'm going to need a few more, a bit extra space, so just move it here. Minus r lambda rho sigma mu delta kappa mu plus r lambda mu sigma mu delta kappa rho minus r lambda sigma rho mu delta kappa mu plus r lambda mu rho sigma mu rho mu delta kappa sigma. Okay, now it's just algebra and make sure that it didn't make any typo in the indices, but you see where this is coming from, basically. I promise you a little bit of algebra here. But we done the hardest part. Okay, so that's what we got. So far, these are general properties of killing vectors. We didn't say anything. We just used the standard definition of the Riemann tensor and the killing condition to get to this equation. Now I'm going to use the properties of a maximally symmetric space. So, maximally symmetric space question?
The equation with 6 indices.
What?
This is an equation with 6 indices.
So,
It's like
what?
it's confusing.
It's confusing, yeah. Look, I told you. There are some algebraic parts here which you need to go very, very slow. I also told you, I think in the first lecture, you're going to go through the entire Greek alphabet in this course. So, I was not cheating. Yes, I mean, it is what it is. You have to do these things slowly, and you see that this is what you get. I mean, I actually did it, right? We just didn't show you. It's not that slowly. It's in 10 minutes, you see that. You go over all the indices. Okay. What does it mean a maximally symmetric space? We basically said that. Homogeneous and isotropic. Homogeneous means that if we go from one point to another point, right, it's an isometry. Nothing is going to change. So, how do I write in terms of killing vectors? You can say that k mu of a point x is equal to 0. Okay, I'm doing an isometry. I'm going infinitesimally from one point to another point. It does not change. And when I do a rotation, right? Say, right? Yeah, but the rotation would be that the first derivative can take any value. So that means that k lambda nu at the point x can essentially take any value. Subject to the killing condition, of course. The way I think of that, the way I understand it, right, easiest to think of it, think of Euclidean space. I'm doing a rotation in Euclidean space. Rotation takes the central point to itself, right? And then every other point would be symmetric, essentially. So k lambda nu would be minus k lambda. So this essentially are the two conditions for a maximally symmetric space. K lambda is equal to 0, and k lambda nu is equal to minus k nu lambda. So, let's plug it in here.
And do this k lambda equals 0.
What?
What do you mean k lambda? It's the vector, constant zero vector.
Yes, it means that it takes a point to itself, essentially. Right, the central point will go to itself. It's not changed. It's an isometry. Think of that for 2 minutes, and you realize it.
Doesn't maximum symmetric space mean the metric is invariant under
The metric is invariant. So every point I go, every infinitesimal change that I go, I get the same result. Right? I see the same metric.
Okay.
Right?
No, you said just for homogeneous translations or notations.
Yeah, that's what I have. That's my definition of a maximally symmetric space.
Yes.
It's not my definition, it's the definition.
Okay. Now how to get that?
Sorry?
How to get to that KU?
Let's see if I can see.
KU is equal to 0. Well, we had to recourse this K. We recourse this space. We had constant vector.
No, at a certain point, if I'm at a certain point x and I'm doing an isometry, it is not changed. Okay, maybe this is confusing. Sorry. Think of it as a rotation, right? If I'm rotating around a certain point, right, then the vector at the point x would be a 0, and the first derivative would be subject to that condition.
Like that.
It takes the point to itself. If I'm having a space and I rotate it,
Okay.
the certain point just takes to itself.
Oh, okay, so, but the translation is also killing with it just takes no point to itself.
But there is an isometry, so I can just rotate it back to the same point, and I hit a 0. Maybe I'm not explaining it that well.
Just the definition.
Isn't the second one just a string equation?
Yes,
The second is the killing.
the second is a killing condition, which is always true.
But how do you explain the first condition?
Again, the simplest way to think of it is if you are just doing a rotation, then the rotation takes the point to itself,
Okay,
essentially.
so
And that gives
for,
you that k should be equal to 0.
for each point you have a rotation. You have a killing vector which is generating a rotation around the point,
Correct.
and that killing vector will be 0 in that point.
Yes.
Okay.
Maybe there is a better way, but I can't think of it right now. Better explanation. Essentially, this is the correct explanation. Okay, let's accept. Don't have to accept it, but you have to understand.
It's not the K, isn't K lambda is not equal to 0, it's not equal to 0 at the point, right?
Sorry.
K lambda is equal to 0 only at the point, right? So
Yes, but
it's not 0 at the 0
let me
at
see
the
if there is a simple way of explaining it. I'll have to think if there is a simpler way of explaining that. I'll try to see if there is a simple way. Otherwise, just have to think of it for yourself. So I'm going to plug these two conditions in here. This is going to give me 0. And this means that the anti-symmetric part has to be equal to 0. So I only have a symmetric part. Only symmetric part left. And then we'll have, okay, if this is symmetric, that means that needs to be equal to the same with lambda and kappa exchanged. So we'll have a minus r lambda rho sigma mu delta kappa mu plus r lambda mu sigma nu delta kappa rho minus r lambda sigma rho mu delta kappa nu plus r lambda mu rho mu delta kappa sigma is equal to the same with exchange of lambda and kappa. So it's a minus r kappa rho sigma nu delta lambda mu plus r kappa mu sigma nu delta lambda rho minus r kappa sigma rho mu delta lambda nu plus r kappa nu rho mu delta lambda sigma. Just means that all the antisymmetric part has to vanish.
Antisymmetric, what is this?
Sorry?
Antisymmetric, what is this?
You know. Basically, if I exchange lambda and kappa, I should get the same result, which is what we want to do. Because you have the minus here. It should be equal. What?
Change lambda and kappa.
Yeah.
It's minus for the
Yeah, but this is what the coefficient that should be the same. Right. Think of it as an yeah, it's just a symmetric part. You think of it in terms of matrices.
Lambda and kappa are both dummies.
Yeah, because I'm well, what that means is
So of course you can exchange it.
no, because this is what multiplies kappa and yeah, essentially this is what multiplies k lambda kappa. So this is the this is the anti-symmetric part of. You can think of it in terms of matrices. All the anti-symmetric part needs to be equal to 0. So only the symmetric part is left. We write this matrix in terms of symmetric plus anti-symmetric. That's it. Okay. Now I contract kappa and mu. And what do I have here? Okay, when I contract your kappa and mu, this is just n. So minus n r lambda rho sigma mu. This I contract, so I have plus r lambda rho sigma mu. This I have a minus r lambda sigma mu nu, and this I have a plus r lambda mu rho and sigma. This is equal to kappa and mu are contracted, so minus r lambda rho sigma mu r kappa is a mu, so r mu mu, this gives me a 0, this is a 0. Here I have a minus r kappa mu, so it's a plus r mu sigma mu rho, so this is r sigma rho, so plus r sigma rho delta lambda mu. And here again I have a minus r mu rho delta lambda sigma. Okay? Now I have again the cyclic sum rule, which means that all three these terms are equal to 0. And then I multiply by g lambda alpha. And when I do that, what we have is the following. Okay. then I did something which is G lambda alpha. So I move that to that side, and I get an n minus 1 r alpha rho sigma mu. And I move those to the other side, and I get is equal to R nu rho G alpha sigma minus R and sigma rho G alpha nu. I promise you it's going to be annoying. Okay, now I use again the symmetry properties of the Riemann, which means that this has to be anti-symmetric on exchanging alpha and rho, right? Because of the Riemann. So that means that R nu rho G alpha sigma minus R sigma rho G alpha nu should be equal to minus R nu alpha G rho sigma plus R sigma alpha G rho nu. And the last, nearly the last part is to take that and multiply by G alpha lambda. Yeah.
That space indents second to last.
Which one?
We contract kappa with mu or kappa and mu with something?
Kappa and mu.
We contract them together.
Yes. You're unhappy, and I can understand. But we're really quite close. I told you, a long path will take us to something which, at the end of the day, is nearly trivial. So multiply by G lambda alpha lambda, and then contract again lambda and mu. And what do you get? So I multiply by G alpha lambda. So I have G alpha sigma, G alpha lambda. Contract lambda with a nu. Right? So I have R sigma rho. Right? And here I have minus R sigma rho, G alpha nu, G alpha lambda. So it's G alpha alpha nu, G alpha nu, which is no. G alpha nu, G alpha nu.
For n.
And R sigma rho is equal to minus R, let's see, G alpha lambda, and then G rho sigma. I'm contracting lambda with nu, so I have an R lambda lambda, G sigma rho, which is symmetric, plus, again here I have G alpha lambda, so that's okay, so I get an R rho sigma. So overall, we end up with the Ricci tensor R.
And those are considered because
Yeah, R sigma rho is equal. So that is that.
1 over n times the Ricci tensor.
1 over n times G sigma rho times R lambda lambda, which is scalar here. So I plug it in here. And I get the Riemann tensor. And I get the Riemann tensor R. Again, I'm changing now alpha and lambda. So R lambda rho sigma nu is R alpha alpha over n plus 1, sorry, n minus 1 times, which is G nu rho G lambda sigma minus G sigma rho G lambda nu. I worked very hard to show you what the Riemann tensor should look like in a maximally symmetric space in n dimensions. Now we're getting close to the end. So the last thing that we have is to use the Bianchi identity, because the maximally symmetric space is everywhere. So if we have the Bianchi identity, nabla mu G mu is nabla mu R mu minus 1/2 R G mu is equal to 0. So we're going to put that inside here. This is R mu. So I have the 0 is equal here I'm exchanging with the sigma, so it's going to be R sigma rho minus 1/2 delta sigma rho R lambda lambda sigma. But this is R sigma rho, that is just 1 over n minus 1/2 delta sigma rho R lambda lambda. Sorry. This is 1 over n minus 1/2 R lambda lambda sigma. What does it mean? Okay. So first, if n is greater than 2, what does it mean about R? It's constant. R has to be equal to R has to be constant. So for n greater than 2, R lambda lambda is constant. So I can write R lambda lambda, because it's some constant. I can simply write this R lambda lambda is equal to n minus 1 times k. K is some constant. And then I plug it in here to get that R lambda rho sigma nu is some constant k times G mu rho G lambda sigma minus G sigma rho G lambda nu. Okay, I told you that I'm going to work very hard derive something which is essentially not that difficult. It's okay? Yeah.
Usually the unit tensors second derivatives.
Correct. This is true for maximally symmetric spaces.
So it's not a no.
Yes. Yes. Now, okay, I'll see if I can find an easier explanation for why this is a condition for maximally symmetric space. Everything else is just in algebra, so you just follow the algebra and try not to get confused on it. There's nothing more than that. Armed with that, we can now go and calculate the Robertson-Walker metric.
No, it's no dependence on the killing vector anymore.
No, I don't need the killing vector anymore. That's what I wanted. I wanted the description of the curvature tensor in the maximally symmetric. I use killing vectors for getting that. Now we can derive the Robertson-Walker metric. So we said Robertson-Walker metric. So we said that observationally, we know that we assume that the space is isotropic and homogeneous in the spatial part, but is changing in the temporal part. Which means that we write the metric, we make a separation between the time part and the space part, the spatial part. Okay. In other words, we write the metric, d squared, as something like minus dt squared plus a squared of t times gij of x dxi dxg. What's written here? So first I use Latin indices because I'm only talking about the spatial part. Second, I make this separation, and I have this a of t, which is called the scale factor, which essentially multiplies the space of the spatial part. So I do let the space evolve in time, which is what I'm saying. Right? A of t, what is the name? It's called the scale factor. And
it multiplies all
the space.
And not every part of it.
Yeah, all the space.
Because of the
it multiplies all the space. All the spaces is multiplied by that, which
אבל כאילו הסיבה שאנחנו לא מכפילים כל איבר בקרוב משלו זה בגלל שהוא איזומטרי והכל.
נכון. It's a maximally symmetric space, so that means that all directions are the same. I do let them evolve in time. That's what it means. That means that the space itself can get bigger or smaller. Right? That I allow. This is a degree of freedom that I allow. Right? But the assumption that it's a maximally symmetric means that they're all multiplied by the same factor. I also make a complete separation. There is no temporal dependence here on the space. Now, so I don't have the, just a second. So no terms like dt dxi.
Why is that?
What?
Why is that?
Right. That's the definition of a co-moving. So that's what I said. It's a hypothesis basically that I make a complete separation between the time and the space. And this is true as long as I'm fixed in the or co-moving with the space. That's what it's called. Right? Are we on Earth co-moving in space?
No.
No, because we are moving. Right? Let's say we're moving around the sun. So our coordinates from here is not co-moving coordinates. But we can compensate for that. Right? If we were fixed in space, that's called the co-moving. essentially moving with the
It's in
space.
large scale of space.
Yes.
What do you mean?
What do I mean? For example, if I'm looking at the cosmic microwave background radiation, I told it's isotropic, but then actually I told it's actually not isotropic because the Earth is moving around the Sun, so we are seeing it Doppler boosted in the direction of motion. If we compensate for that, then we have to compensate for the motion of the Sun.
So we take
Around the center of the galaxy.
a chunk of the universe and then in the center of mass, moving around.
Co-moving with the coordinates means we're not moving relative to the coordinates. Okay? Now we are moving around the Sun, so relative to the coordinates, which I didn't say what they are really, but when we say cosmic microwave background, for example, it is isotropic. If we are not moving. If we are moving, then of course we're seeing the Doppler boost. One side would be bluer and the other one would be red. Yeah.
How can this metric allow the universe to become smaller? You have a
Wait.
square.
Wait. It's completely general thing. Right? I mean, basically, co-moving means that it looks isotropic. If it's not co-moving, it doesn't look isotropic. Okay. Now we have that, and I'll just we have this equation here, but this is only true for the spatial part. So I'm going to put it with an 3 here, and instead of Greek letters, I'm going to use Latin letters. So I, J, K, L is equal to some K, right? Some constant, which I don't know what it is. G, I, K, G, J, L minus G, I, L, G, J, K. And the Ricci tensor are JL, 3 dimensions, is what we just derived, n minus 1, K, G, J, L. Since n is 3, this is equal to 2K, G, J. Okay, now, if we say that the space is maximally symmetric, then obviously it is spherically symmetric. If it's spherically symmetric, that means that you can use what? Spatial symmetry. We can use the derivation we did for the Schwarzschild metric. It was based on isotropic, right? Take grab the mass from there, basically. So maximally symmetric. It also means spherically symmetric. So from the Schwarzschild metric, we have again just a spatial part. So d sigma squared, g I j dxi dxj. We can write it as e to the power 2 beta of r, dr squared, plus r squared d theta squared plus sine squared theta d phi squared. Right. We know this holds for a spherically symmetric metric. So it must hold here. Now, again, components of the Ricci tensor, we already did when we calculated the Schwarzschild, so I'll just remind you of that. So, for the Ricci tensor, right, just from the Schwarzschild, use the Schwarzschild, and alpha is equal to 0, and d0 beta is equal to 0. There's no derivative, time derivative, and we end up with an r113 is 2 over r. d1 beta, r22. 3 to remind us this is 3 dimensions. E minus 2 beta, r d1 beta minus 1 plus 1, R 3, 3. 3 is E minus 2 beta, R D1 beta minus 1 plus 1 sine squared theta. This is all copied from what we did for the Schwarzschild metric.
What is alpha?
Sorry?
What is alpha? Alpha equals
It was the alpha was the what we had for the time. Then alpha multiplying the time and then beta the r. So we'll just go back. It's the same equation I'm using, the same calculation, and I get the same result for r. So I have these equations here. So I set these equations. I compare them. What I have is R11 3 dimensions, right? Is 2 over R U1 beta, and that is equal to 2K G11. What is G11?
1.
No.
It's a e to the
2 beta.
This is 2K e to the power 2 beta of R. And R22 e minus 2 beta R D1 beta minus 1 plus 1 is equal to 2K G22, so this is 2K, and G22 is just R squared. So these two equations, which is pretty straightforward, you multiply by e to the power 2 beta, divide by R squared, and you end up that beta is equal to minus 1 half log of 1 minus k r squared. So plug it into the metric. Get
K could be positive or negative.
I don't know, k is k. And we get that ds squared.
Wait, but if K is positive, then
Wait. Hold on a second. Minus dt squared plus a squared of t times dr squared over 1 minus k r squared plus r squared d omega squared. This is the Kosmologya metric. Sorry?
How do you get the solution to the equation?
What is that?
How do you get the equation is equal to
That's just a basic algebra. So I leave it for you. Practice that. And just use the. Okay, you saw the logic. I use our derivation here that we did for maximally symmetric. This is true only for maximally symmetric space, right? That one and that's just we derived that when we talk about this when we derived the Schwarzschild metric, which is spherically symmetric.
it's unique?
What?
It's unique.
Sorry?
It's the spatial part.
This is the special part.
It's
Let's see.
unique.
Let's see.
wait, doesn't if you solve an ODE, don't you need a constant?
Sorry?
Don't you really have a free constant that you can?
I have here two things. I have A and I have K. Right. A is a scale factor that multiplies all the.
But K is not a new constant. It rises up from.
We got K when we derived the.
But when you solve an ODE, don't you have to get another constant?
So I did not specify what is K. Just say K is a constant. That's when we did all the mathematical derivative. We said K is a constant.
אבל אם יש לך מערכת משוואות, ה-K הוא כבר קבוע בתוך המשוואה, מערכת משוואות אבל...
אני לא יודע מה הוא K. 18, לא יודע מה זה מספר. But the thing is, related to that, I actually don't really need to know what is the exact value of K. Why? Why I don't really care about the exact value of K? What?
אבל הדבר הזה הוא סימטרי ליד הזאת בכלל.
מה?
למה הדבר הזה הוא סימטרי ליד הזאת?
תכף תראה למה הוא סימטרי.
למה הדבר הזה סימטרי ספק, אבל למה נזז כל ימינה?
Slowly, everything will be fixed. So. Now we can rescale. Right. Rather than K, we can normalize it. K over K. And then R, we can normalize to square root of K times R. And then A, we can normalize to A over square root of absolute value of K. What happens to this equation when we do that?
1 plus or minus half.
What happens? Nothing, it's invariant. The equation stays the same. If I rescale, if I do this rescaling, then the Robertson-Walker metric is invariant. Yeah? So what does it mean? What?
There's a killing vector.
No, we don't need a killing vector. So what are the interesting values of K really?
1 and minus 1.
Or 0.
And 0.
Oh.
So that means that we only care about 3 values of K. Everything else can be absorbed by rescaling the coordinates. Right? So we care about K can be equal to plus 1 or minus 1, 0, and plus 1. We only have 3 options. Now, universes that have that, they have names. So K equal to minus 1. How do we call them? No. What? What? These are called open. K equal to 0. Flat. K equal to plus 1. Closed. Now let's see. If K is equal to 0. What do we have here? Let's look just at they call this sigma. Sigma, these sigmas. So just the spatial part. So the sigma squared is a what? dr squared plus r squared d omega squared. What is that? What? This is a flat space written in spherical coordinates. So I can write it as dx squared plus dy squared plus dz squared. This is really a Euclidean space, flat. Right. Well, it doesn't have to be exactly Euclidean. There are a little bit mathematical subtleties, but the idea is quite clear. I mean, I thought they were going to work very hard to get some result which is trivial. Right. So the first option we have, flat space. The second option we have, right, if we have K equal to plus 1.
Then we have a
if k is equal to +1, then we can write down R is equal to sine of some function chi.
That has to be between -1 plus 1.
What?
Because it must be between -1 plus 1.
Yeah.
So you don't divide it.
Right, so I have dr squared over 1 minus r squared. Right. So what is dr squared over 1 minus r squared?
What's that square?
dr squared is
Cosine
cosine,
chi
right?
d chi.
That's right. 1 minus r is sine chi, right? dr is
d
cosine chi.
You need just d chi square.
Right. So I end up that d sigma squared. First the chi squared. So I have that d sigma squared is d chi squared. Now I have plus sine square chi d omega squared. What is that? It's a sphere. Right. It's a three-dimensional sphere.
And this is theta and this is phi.
That fire here.
Yeah, but in a sphere, yeah.
Yeah.
It was
It's a three-dimensional sphere. It's a 3D sphere. Right.
How does this view?
זה כמו של ספירה דו-ממדית, רק כאילו שלושה
If it was a two-dimensional, how do you describe a two-dimensional sphere?
d theta square plus sine square theta square.
So what's it
Right.
like? That's a 3-term. It's not 3D sphere, it's a 3-term. That's the correct name. I don't know how to visualize it. Just have to.
It's not a
You
ball.
don't need to
What?
imagine
Not
a
a
free
ball.
ball.
No, no.
A free
No,
ball
it-
underneath the edge.
It's the envelope of
It's-
four-dimensional.
Yeah, exactly. It's like the ball that you're thinking of, right? You think of the surface of a ball, right? It's a two-dimensional sphere, which encloses a three-dimensional space, right? Here it's a three-dimensional.
So it's enclosed a four-dimensional ball.
In a way, yes, it's the surface of a three-dimensional.
In the 4 dimension.
Yeah, but this is a three-dimensional. This is a 3-term, right? So I'm not sure how to.
The envelope of this one.
But this is a name, by the way. Geometry that looks like that, or space that looks like that. You might have heard of it. Let's call it the Sitter space. Sitter space. Okay. And then the last option, we only have 3.
So now you just times hyperbola.
Exactly. So if k is equal to -1,
Just r equal to sine.
then r is sine hyperbolicus some function psi. Then we have d sigma squared is d psi squared plus sine hyperbolicus squared of psi d omega squared. So the same way as a ball is a maximally symmetric space with constant positive curvature. This would be a maximally symmetric space with a positive negative curvatures and so forth. That really is difficult to visualize. It's like a saddle, right? What is saddle thing?
But the saddle is not.
It's like a saddle at every point.
It's not a symmetric. Or it is.
Basically, at every point has
Like the south, but how the saddle is symmetric.
what?
Because
Now, what I want to this is that I want to show a negative curvature. It's not symmetric.
so
This is a space which is symmetric, obviously, that's how we constructed it. It's a maximally symmetric with a negative curvature. I really don't know how to visualize that. And of course, this is closed. This is going to extend forever. There's no limits. Right? The flat is sort of a boundary, that's all. It's a boundary between. Yeah? So if this is the sitter, this will be called anti-de sitter. Yeah, I put it. It's a bit. I think you have to use your imagination. Think a bit about it. Okay, so I told you we're going to work very hard. I don't know if there is a point. Okay, the next thing is to derive Friedman equations, but that again requires some math. So I don't know if it's correct to start now. A few minutes left to the end of the class. Let's go over what we did here, because I told you, unfortunately, today is very heavy in math, but that's the last part, which is really heavy in math, of course. The bottom line is, we worked very hard to get to this bottom line. And the bottom line is actually very simple. Right? We derive the space, which is maximally symmetric in its spatial part. And maximally symmetric, you end up, there are really only three options. Right? Flat, in the space, Euclidean, spherical, 3D, not 2D, and the opposite of spherical, so negative curvature. All the coordinates are multiplied by the scale factor AFT, so they can change in time. We allow them to change in time in the same way. They are all multiplied the same way. And there is this unknown, which we got during the derivation when we concluded that the Ricci has to be constant. And we don't know what its value is, but really we don't care because everything can be absorbed into the physical, absorbed into our definition of the coordinates. So we only have these three cases that are of interest. Everything else is just scalable. Do you know which universe we live in? I'm going to tell you now.
Do you?
Discuss that on the next class. Sunday. I do. All right. Questions? Questions?
So the answer would be on Sunday.
Maybe. If I want to give it to you. Come on Sunday. Any questions? Yes.
In all the examples of the three universes, the dt is sort of like not changing. The G00 is 1.
Yeah, that's how we constructed it. Essentially, yes. So we want to have a separation. Again, I can rescale it, but it's meaningless. Right? The important thing is that I don't have any cross terms. I don't have any term which looks like dt dx. Okay? And again, this is a definition of essentially isotropic and homogeneous in the co-moving frame, if I'm not moving relative to the universe.
And the A function can be any function.
We'll discuss that.
Sorry?
We will discuss that. It cannot be any function. There is one thing which we did not do, which is what? With all the math that we did today, there is one thing basic which we did not do. Yeah, we did not use Einstein's equation.
You did the Einstein.
No, I used the Bianchi identity.
Yeah.
Bianchi identity, I don't need Einstein's equation for it. Bianchi identity is an mathematical identity, which is fine. To get AT, we'll have to solve Einstein's equation. That's what we're going to do on Sunday. But what we did today was, 90% math. The physics was just in the last 10 minutes of the class. This is entirely math, just looking at the properties of Killing factors. And I'll try to see if I can think of a simpler example, or not simpler, intuitive example how to do how to get it beyond the way that I think of that you have these isometries. Maybe there is something, I don't know. I searched a few times, I couldn't find it. Maybe something will come up to my mind over the weekend. All right. Okay. If no further questions, I am doing a big effort to find some time to summarize to you the precession from classical mechanics. Just because I think this is something which is it's not very difficult. It's actually pretty straightforward if you did first and second year mechanics. Surprising you didn't do it, and I think it's important that you know. I just need to find the time to wrap it up somehow. All right. See you on Sunday and have a good weekend.